Okay, welcome back to COSM 4111. This is the HVAC CFX simulation. We start a new part in Solidworks. Select part, okay. Wait for that to start. And the basic layout of the room is that it's 3 meters by 3 meters by 2.5 meters high, and it has a vent in the roof, an inlet in the roof, a vent in the side wall, and 2 windows and a door. So if we start off with the front plane or XY plane, and so our height is going to be in the Z direction. And if we start by going to sketch, create a corner rectangle, and so we start at the origin and draw an arbitrary rectangle, change our units to meters, kilograms, and seconds. And if we look at the properties here, okay, smart dimension that. So you can see that's way too small. We want that to be 3 meters by 3 meters. So change that to 3. And we smart dimension this as well. That's 3.91. Just want to knock that down to 3 meters. And if we fit that, zoom to fit. We have the basis for our floor now, and we're going to extrude that. Then select that sketch and complete it there. And we are going to use extruded boss to extrude that in the Z direction, positive Z direction, through 2.5 meters. Like units are meters. Extrude that, and we have the basis of our shape. Just try and rotate it into a more usable orientation. Okay. Okay, the first step is to put a small vent in the roof here. So we see we have front plane there. We do this by imprinting the face. So we'll draw a small little rectangle in here and set it to the right size, and then we'll imprint it on this face. We return to sketch now. We have the front plane selected. We're going to draw another rectangle. I'm going to draw a fairly arbitrary small rectangle along there. And if we go to the parameters of that, we want to get that to go from x is equal to 0.05 and y is equal to 1.3 as one corner, and x is equal to 0.15 and y is equal to 1.7 is the other corner. So next, change that to 0.05, and for the local coordinate system, this is going to be minus 1.3. The other corner is minus 1.7. And then x here will be 0.15. That's the correct thickness. And the rest will adapt. So that gives us our inlet there. Let's apply that. And now we want to project this shape here onto the ceiling. So we select that. Select Sketch 2. Go to Features and select Curves. Split Line. This line is going to split this plane here. So Sketch 2 is our split line. This is our target here. Single direction. See, single direction is pointing downward, so we want reverse direction. So it's pointing upwards like that. If we see what that does. A nice upshot of that is that we have a small face here imprinted on the top. So next up on this wall beside it, we want to put both a window and an outlet down here. So that'll be two rectangles, each of which are about 1.5 by 1.5 high by 1 meter wide. So if we select our plane here, I'm going to do it on this plane and project it onto this face here. It saves me having to create a new plane for that. For this. So if we select one face here, we're going to do the window first, in around the middle of the plane here. Once again, we can set the dimensions as needs be. And we see that down here the corner, the dimensions of the vertices come up. So if we change this dimension to 1.25, change this dimension to minus 1.75. And stays at 1.25 here. This goes to minus 0.75. And then this changes to 1.75. We should be fully defined after that. We have this rectangular window in this plane here. Let's generate that. And then say we have our outlet. It's going to be down this corner here. It's going to be down in this corner when we project it onto this face. So same plane, top plane. We draw another little rectangle. Just keep it in and around the bottom corner here. Once again, the dimensions are arbitrary. We'll set them in a minute. We'll start with x is equal to 2.55. And y is equal to minus 0.15. The other y, which will give it its height, is minus 0.55. So we still haven't really given it its proper thickness. And we set this here to 2.05. And that has set the thickness of the dimensions. We can save that. So this sketch then is these two here, which will now project onto the opposite face. That's sketch 3. Go back to features. Curves, split line. We're going to use this to split this face here. We use sketch 3 to split this face here. And let's see, single direction. Seems to be the right direction. We'll see if it works in a second. Okay, it's given us these separate faces in here on this one. So our window and our outlet. I'll take that to a slightly better view of here. Select the right plane. And we're going to draw a window similar to this, but in this plane here. So we select rectangle, corner rectangle. So I'll try and do something similar to this one here. And we set these parameters on it here. Say minus 1.75 to minus 0.75. And so the thickness is given by the y's here from minus 1.75, minus 0.75 up to minus 1.5, which should in fact be 1.25 up to 1.75. I'll change this to minus 1.25. Get this more one centered on here. And change this to minus 0.75. That'll give us the correct height there. So we put them in this order here. And generate our window. Okay, and we generate that sketch as well. We go back to features, and curves, split line, and project onto this face here. So our face is there, our selections, let's go here. Okay, we'll select the sketch 5 before we do it, and then curves, split line. And then we can select the face. Let's try single direction and reverse direction. Doesn't really matter. And generate that. And that gives us our separate face inside here. Let's try and rotate that view around so we can see this opposite face here. Where we're going to put a door down on this side, which is 2.3 meters wide and 3 meters high in this corner here. So if we draw, it's 2.3 meters high. And 0.7 meters wide. So if we try putting in, select the correct plane first. That one. Select the right plane here. We'll imprint it onto this face here. We sketch a rectangle. And so we want it 0.7 wide. So y is equal to 0.7 and 2.3 meters high. That's approximately it. Generate that. Let me try putting a dimension here. So now we change that to 0.7. Okay, that hasn't put it in the right place. And we try dimensioning the height as well. So another smart dimension. And that's 2.3 meters high, which is correct. So we generate that. That's our last act here then, is to take this sketch, go back to Features, Curves, Split Line, take that sketch 6, and imprint it on this face here, and, with a reverse direction. In this case, whichever way that arrow is pointing is the best. And we see the door generated on that face there. One last adjustment I want to make to this, and that's to increase the size of the inlet here. That's so we can reduce the flow velocity in for the same flow rate, which will make the calculation more stable, which we'll see a bit more about in the simulation part of this exercise. So I take the view from above by clicking on the Z-axis here and zoom in on that. So I'm going to increase this from 0.1 meters to 0.2, increase this from 0.4 meters to 0.8, give an overall increase in the area of a factor of 4. So if I click on the sketch associated with this split line and hover over it and click Edit, and so there I have, this is the length of 0.1, change that to 0.2 meters, and change the length of this from 0.4 to 0.8. And you see this side hasn't moved here, so I have to change this so it's in the center of the room again. So you see this length here is greater than this length here. So I insert smart dimension, vertical dimension, which is the distance between this line and here. It's equal to 1.3. So 3 meters minus 0.8 is 2.2, so half of that would be 1.1. So change that to 1.1, and it pulls it down there. So if I click that and create that, and now I have the enlarged inlet there. So it's adjusted it as such. So now I go File, Save. Make sure that's saved in. Make sure that's saved somewhere. That's you have access to on your, preferably on your OneDrive. And now we're going to move to the simulation part, and we go to simscale.com and start simulating now. I'm going to create a new project here. I'm going to call it something, HVAC something. Quick description. I put in flow of air in a room with aircon. And create a project. And so now we need to import our geometry here. Click on Import from Computer and go to the directory that it's in. So I select the file, the Solidworks file that I just saved there, and open that and import it. So I'm ready to create the simulation. I'm going to use convective heat transfer as my model and create simulation there. And we see the usual menus along here. And we need to set up the direction of gravity first. That's in the negative Z direction. So I go into Model, change GZ to minus 9.81 meters per second squared. And that gives me my vertical direction there. I'll now reorient it so we have a roughly isometric view. That's our inlet here, and we have our doors and windows and so on. I change our materials, select air there, and click the defaults for the properties. Okay, so we move on to the boundary conditions. We add them in sequence. So add the first one, which is going to be the inlet. Change the name to inlet. Our boundary condition is velocity inlet, and we just need to set two components of the velocity. So we're going to set an x component along this direction of 0.3 meters plus 0.3 meters per second. Just give us a component along the ceiling like that, and also a z component downwards of minus 0.15 meters per second. That will give us about 30 degrees into the room. Then change that to inlet, and our temperature, set that to 16 degrees C because it's cooling air. Change the radiative behavior to opaque and save that. Add another one, a pressure outlet. Oh, sorry, we didn't select our face for this, so we just select that. Our outlet goes here, and it's a pressure outlet and atmospheric pressure. The outlet, once again, set the radiative behavior to opaque with an emissivity of 0.9. So that's the flow conditions set. Next I'm going to set the conditions at the windows. There are two windows, here and here. And so I add a wall boundary condition here. And no slip condition. Temperature type, I'll change that to an external wall heat flux. Add a heat transfer coefficient. I'm going to set this equal to the U value of the walls, which is recommended to be 2 or less. And an ambient temperature of 27 degrees C. And I'm going to have an additional heat source entering the room through the wall via radiation at the bottom here. So I'm going to change the behavior to transparent, and I'm going to have 100 watts per meter squared radiation coming through the windows. I can set an initial boundary temperature here. I'm going to set it to 27 degrees C. I'm going to set the general initial conditions for the whole room as being 20 degrees C, so basically too hot. And then I'm going to have see the effect of the cooling air coming in. And then set our geometries to the 2 windows there. And select that. Those windows are set in 2 external walls here, so it's a corner office sort of building. So I'm going to have these 2 walls here as external walls with heat loss to the outside along them. So that's my next boundary condition. So they are walls. I'm going to call them external walls. And I'm going to set an external wall heat flux on them. And a recommendation for external walls is that you have a U value or heat transfer coefficient of 0.3. External temperature 27 degrees C. And we'll have initial boundary temperature of 27 as well. The radiative behavior is opaque. And we can leave it at that. And we just need to select this face. And this face is our external walls. Every other surface we're going to count as being an internal boundary. So including the wall, we're going to assume that's internal as well, and that they all have the same temperature on both sides, roughly the same temperature on both sides. So you're getting 0 heat transfer across them, so we'll set them as adiabatic boundaries. So I'm going to create another type of wall. I'm going to call it internal. And for the temperature type, just set that to adiabatic. And radiative behavior as opaque. Now I just need to select the surfaces. So I'm going to include the ceiling here, an internal ceiling. I'm going to assume the floor, which is the ceiling of another room, and this wall of the door, and that. So this will simplify it somewhat. And so that gives us so our inlet there. I'm going to change the name of pressure outlet to just outlet. There. And I'm going to change these to name to windows. Then we have our external walls, those 2 faces, and internal walls as well. Also want to set my initial conditions here. So I'm going to set the temperature for the whole room as 27 degrees C. So I'm assuming it's basically at the external temperature, outside temperature as well, and needs to be cooled down. And I'm going to set all my velocity components to 0 meters per second, so still air. That'll be changed when air starts to flow in. Essentially, we're assuming a start condition where the room is at 27 degrees C and still air. Next thing I want to do is create a point representing the position of a thermostat within the room. I'm going to put it along this wall here. I click on Geometry Primitives and Point. I can create a point at a particular location. And for this case, it's going to be 2.98, which is along this wall here, just off this, just short of this wall. So this total length from here to here is 3, so 2.98 is 2 centimeters off that wall. I also need y equal to minus 1.5, which will take us into the center of this wall here, and z then 1.25 off the ground, halfway off the ground, and it'll just give us inside this wall here. So that's our point there. We'll assign that properties in a few minutes. So the next thing I want to go into is simulation control. So I want to run this simulation for 180 seconds for 3 minutes. So we're starting at 27 degrees C. We're going to see how much cooling we get over 3 minutes. our delta t is our time step. So we want to be able to use relatively large time steps. So I'm going to set this to 2 seconds and allow adjustable time steps. The courant number is a non-dimensional variable, and basically it represents the number of cells that the flow passes through in a time step. And then this should be less than or equal to 1 all throughout the flow field. So I set the maximum courant number equal to 1. And maximum permissible time step, I'm going to set that to the same as the delta t, time step 2. And right control is number of time steps. I'm going to write it out every 5 time steps. So that's every 10 seconds. I'm going to end up with 18 sets of results. And the rest can leave as it is. That's our simulation control. Also want to go into result control and select probe points. So I'm going to add a probe point, and I want that to be at 0.1, and I want to write out the temperature at that of every interval. So we'll have the results at that point plotted out at every time step. Save that. We also need to maintain stability. By default, this will be mesh fineness will be set to 5. I'm going to reset it to 3. That will make the cells larger, and this means that as the flow moves down from the ceiling, it means it moves more through less cells per time step, and will improve the stability of the calculation. So I change that mesh fineness from 5 to 3. Select that. So we should be ready now at this point to start our simulation run. If I add a simulation run, oops, I forgot to define gravity there. Mustn't have saved that, so I'll cancel that. Go back to model and set my gravity in the z direction of minus 9.81 meters per second squared. And then we go back to my simulation. It's not giving me any errors now. I will now set that running. You can see how the calculation is proceeding if you go to convergence plots, residuals. It'll show you the normalized error in the equation. If that's generally going downwards or fairly low, of the order of 1e minus 4, 1e minus 3, then we'll be happy enough with the level of accuracy provided. You can also go into probe point plots from run 1 and select temperature. That'll show you the temperature at the probe point, and you can see that that's dropping as more cold air enters the room. The whole entire run is going to take about half an hour, so you'll have to wait for that. Okay, so that took just over half an hour in my case, and we're looking at the residuals here. Seeing a decent drop in the level of the residuals or overall error in the calculation, so happy enough with that. You can also see output from the probe point. You can see it drops steadily to 298.9 degrees, which is a decent drop, but still quite warm. Would need to run for significantly longer to get it down to a reasonable room temperature. So the next thing we're going to look at is the results. If we look at solution fields, that'll take a few seconds to load in. Okay, we're looking down on the room here. What I want to see is cutting plane through the center of the room here. So that's a plane, constant y, and rotate it around a bit, and change the cutting plane to y there, and make the overall body, make that invisible. Click on right here to straighten it up somewhat, and you can see the stream of, if we color it according to temperature, you can see the stream of cooling fluid coming in here, and we can, clicking on play here, we can see a simulation of the temperature distribution. And you can see that the cooler orange area is spreading out slowly through the room. So you'll see a continuous drop in the temperature as more and more cold air enters the room. Some of that will be offset by the fact that you have heat gains through the fabric and through the windows, but you get a good idea of the flow pattern within the room from that.